Hi there, my name's Chris Collison, and today we're going to talk about pressure in liquids, and this is ahead of the Avogadro's number lab that we're going to do in Chemistry 155. So let's take a look at pressure in liquids and see how this applies to our particular experiment. Thanks for listening. So pressure in liquids covered for Chemistry 155 in the Avogadro's number experiment. We start with a basic idea, Torricellian pressure. And we start with an idea where the pressure in a liquid is equal to rho times G times H. And the rho here is simply the density. And we're used to seeing this density in grams per centimeter cubed. But we could also write this down as kilograms per meters cubed. We'd have to do a conversion. The numbers would be different. They'd be off by a factor of 1,000. And then G is the acceleration due to gravity, which is always going to be 9.807, and that's meters per second squared. And then the H in here is the height of the particular liquid that we care about. And when we're working with torrs, so we now know the torrs comes from Torricelli. It's a unit of pressure, and it's really embedded in this particular equation. Okay, so this typical in System International units, this distance, of course, would be in meters. So ultimately, if we think about the diagram that we have over on the left-hand side, we actually recognize already that 1 atmosphere is measured as 760, and that is millimeters of mercury. And how's that converted into a pressure? Well, so again, we've got the density of mercury, and the density of mercury, by the way, is equal to 13,546, and that's kilograms per meter cubed. So there's our density. So we're going to multiply that by 9.807, and that's meters per second squared. And then we have, of course, the height of the mercury, which would be 0.760, and that's meters. So that comes out to be equal to 100,963. And the units there would be kilograms. We could write it as kilograms per meter per second squared. If you go through, we've got 2 meters that are on the top here, and we've got a meters cubed in the bottom. So we could write that as kilograms per meter per second squared. But I'm going to write it actually as kilograms meters per second squared in the numerator per meter squared. Why am I doing that? Well, the other thing to think about here is that force, Newton's second law, is equal to force equals ma. So this is a mass, this is in kilograms, this is an acceleration, so this is meters per second squared. So that's a force, and of course pressure is equal to force over area. So we'll take the units of force in here. Here's our units of force. And we're going to recognize that units of force divided by the meters squared of area. So the units of area are meters squared down here. And what we end up with is a unit of pressure. So 100,963 kilograms meter per second squared, that's the force part, divided by meters squared, that's the area part, and ultimately this is equal to, this same unit is equal to the Pascal. So this is Torricelli's experiment in a nutshell. So why is that relevant to us in this particular experiment? Well, we're going to effectively run an experiment in the same way. It's just now what we're dealing with is atmospheric pressure. So supposing on a given day we measure the pressure the air pressure on that day as being equal to, let's say, 767 millimeters of mercury. Okay, and this pressure is this air pressure that you see in this figure, and it's equal to the total pressure that we find in the tube of water. So the height here now, by the way, is going to be the height of water. In our particular experiment, we have a height of water, and this ends up being 600 millimeters in this example, and that's 600 millimeters of water. Okay, so what we also have is we have a certain amount of air plus the water vapor pressure. So we remember when we have some water sitting in a beaker, it gives off a certain amount of pressure that's released, or that pressure comes from the water molecules evaporating at that particular temperature. So what we have in here now is a pressure in this red area here that is the air pressure. So there's going to be some air presumably that's left inside this particular tube, plus the water vapor pressure. Okay, so what we have to think about here now is that the pressure, 767 millimeters of mercury, is actually equivalent to the pressure of the air in this tube. So we're going to put down the pressure of the air in the tube plus the pressure of the vapor pressure. It's the vapor pressure of water plus now the 600 millimeters of water. Okay, so all these things are going to add up. Here's the 600 millimeters of water. Okay, and that pressure, by the way, the pressure there is going to be equal to the density of water. So that's rho times G times H. Okay, so we can do that conversion. We can figure out, in fact, we can convert from, if we're going to use units throughout that are going to be units of torrs or millimeters of mercury, then we also want to convert millimeters of water into millimeters of mercury. We can think about this in another way. So remember, of course, that from the previous slide, but now in slightly different units, 13.546, and that's grams per centimeter cubed. That's the density of mercury. Okay, so there's our density multiplied by 9.807, that's meters per second squared, multiplied by millimeters of mercury. This is what we're trying to convert into. This is what we're trying to find. Well, that is equal to the density of water, 1 gram per centimeter cubed is our density of water, multiplied by, again, 9.807 meters per second squared, multiplied now by the, in this case, we know it's 600 millimeters of H2O. Okay, so if we want to convert into millimeters of mercury, what we're going to do, well, we recognize in this equation that these two terms will cancel. So if we want to find out millimeters of mercury, it's simply equal to the height of the water, so it's the 600 millimeters of H2O multiplied by the density of water, 1 gram per centimeter cubed, divided now by the density of mercury, so 13.546 grams per centimeter cubed. Okay, and that is going to allow us to convert from this 600 millimeters of water into a unit that is millimeters of mercury. So we're going to do this calculation in here. We're going to add up the vapor pressure of water. We can look up the vapor pressure of water at 24 degrees Celsius. We find that the vapor pressure of water is 22.4, and that is millimeters of mercury. And we also have, of course, the air that's already in our tube. In fact, we actually can calculate the pressure of the air in the tube that already exists before we start running our experiment. And this particular slideshow will be very important to you as we go through the Excel spreadsheet for this course. So in any case, this is basically a quick introduction to pressure in liquids, and we're thinking about converting between pressure in water as a liquid based on the height of that water, and converting that into millimeters of mercury, which is a standard unit for pressure. Thanks for listening. We'll see you in the Excel spreadsheet, and some of these calculations will start to make more sense.